Hello from the Czech Republic. My name is Marta, and in my today's presentation, I'm going to talk about optimization of moldable workflows under incomplete performance data. Oh, yeah, now it's better. So on this slide, I would like to explain what moldability means and why it is interesting for me. Workflows or task graphs, as you can see here. Can you see my cursor?
Yes, just about.
Yeah, okay, so workflows or task graphs represent executed tasks and their relations. Those workflows include heavy parallel tasks being able to be executed over multiple computational nodes. And the way how we select the number of execution nodes for each task in this workflow impacts the final mapping of task to computational resources, as you can see here. In other words, it has an impact on the overall execution time and cost. The optimization stands on a knowledge of strong scaling of each executed task, as you can see here in the top in the graph. However, we have to keep in mind that scaling is never perfect. So adding more and more resources will increase the cost of the computation, but the impact of on the lower computation time will not be the same. You can see very simple illustration here. From the user's point of view, running complex simulations on HPC may be tedious, time-consuming, and also impracticable for many users that don't have IT knowledge. This motivated us to develop a tool that is used without a command line. Users don't have to specify the execution parameters for each task in the workflow and don't have to monitor their calculations. They only may express their preference whether they want to minimize either the computational time or a cost using, for example, such a fancy slider. And this tool provides automated, effective, and failure-free task execution. To be able to provide such optimization of the workflow executions, we implemented 4 performance modules. Optimizer, this is the first module. This module stands on the genetic algorithm and finds execution parameters based on task inputs, and it uses collected performance data. In practice, we are not able to hold all performance data for all input possibilities. But I will talk about it later. Here you can see interpolator. It finds its place when we are I will say it in other words. Interpolator finds its place exactly when we are not able to hold all performance data in our database, and we need to somehow predict how our code scales. And interpolator estimates the execution time and cost for a given amount of resources. Here on this very simple picture, you can see how those modules communicate with each other. I will move back. Next, evaluator works very closely with optimizer because it calculates the quality of evolved schedules using built-in cluster simulator. And finally, collector updates the performance database after each successful run and implements some kind of reinforcement learning. So the input for the optimizer is the input, the user input. Usually it's some kind of file that represents the workflow and collected performance data. And the output of the optimizer is execution schedule that can be used or is used for the task setting. And this shows the mapping of tasks on the cluster. Now I'm going to move to experiments that were done in the paper. The first goal was to improve the built-in cluster simulator in the evaluator module. So far, it used one-pass PBS-based simple simulator. This simulator didn't implement the backfilling, so it was a thing that I wanted to implement because it's commonly used in PBS batch schedulers. So as you can see in this picture, tasks come to the HPC system and are executed in the same order as they are defined in the workflow. So 0, 1, 2, 3, 4, and so on. And without backfilling, tasks number 5 and 7 would have waited for tasks 4 and 6 to finish. But with backfilling, those tasks may overtake task number 4 and 6 and reduce a size of so-called shadow windows, as you can see in this picture. The second goal was to include the estimator module to the optimization process, because so far it wasn't implemented. I used the whole performance data sets. And what I wanted to do with these goals was to discuss the similarity of workflow execution schedules to the one that were executed on a real HPC cluster. As a reference HPC cluster, I use the Barbara cluster at IIT for Innovations. And I discussed the error reached by the interpolation techniques. In my experiments, I used 2 medical application workflows. One is HIFU prostate cancer ablation, as you can see in the video on the top. And the second one is a neurostimulation. In those workflows, heavy simulation tasks are interlaced with lightweight data processing tasks. On this slide, you can see how implemented backfilling affected the execution schedule. So on the top picture, you can see the execution schedule where the backfilling was switched off, and the make span takes 32 minutes. On the schedule below, you can see that make span takes only 26 minutes, and the backfilling is switched on. So you can see that in this case, we can simulate the execution more accurately. And on this slide, you can see how it was in a real execution. You can see that the real execution is a bit longer than the simulated execution where the backfilling was switched on. But it is usually caused by some waiting time between tasks. So I'm not sure if you can see it, but here you can see that the black line is very thin. So, for example, task number 11 is executed immediately after 10, but in a real execution, you can see that there is some waiting time. So it is caused by this, but the difference is very low. To conclude this experiment, I may say that backfilling didn't impact the results significantly, but this may be also caused by the workflow structure. So the workflow structure doesn't give much space for backfilling. The error I've got between developed and real schedules fits within a 13% margin, which is great from my point of view. Next, I'm going to talk about my second experiment, where I was investigating interpolation methods. So in the first case, I did some experiments where the scaling was interpolated for only a single domain size. Since the K-wave code scales quite well, the linear interpolation gives promising results with mean relative error under 4%. On this slide, you can see how I calculate the mean error. Next, I also did some experiments on the domain size that hasn't been seen before and is fully interpolated based on different domain sizes. In this case, I've got some quite nice results using the quadratic interpolation, having the mean relative error of 10%. In reality, a safety gap of 10% of the execution time would always be added to the predicted execution time because hardware itself may impact the execution time. So I call it safe execution. It's better to make it a bit longer than, well, if I underestimated, the task wouldn't be completed, so it's better to add some time. Okay, so here I try to evolve execution schedule for the workflow of 40 and 80 tasks of the workflow structure that you can see in the middle. This slide is quite heavy, so I try to explain it. Okay, so I used, well, now let's move to the left side. So I used performance data of a cube domain where each side of the domain had 1,000 points for a reference. I used a data set where all points, it means 32 points are known, and then two data sets where only 8 and 16 points are known. Since the experiments were done on the static allocation, I used Makespan to compare the evolved workflows. You can see that I've got the highest error of nearly 13% for workflows of 80 tasks, where only 8 from 32 points were known. But in a case, we knew 16 from 32 points, the error dropped down to the error of only 2%. You can see it here in the table, and I think it's quite nice result. And now let's move to the right side. This is another part of this experiment, and I here I try to predict the whole domain. I picked a cube of 800 points per edge. The first row in the table is again the reference one. So the interpolation wasn't used in this case. And the second row shows the case where the quadratic interpolation was used, and the error I've got is between 10 and 15%. So this is, I think, also quite nice. So, okay, on this slide, I would like to conclude my presentation and say something about the future work. The optimization implemented transfers multi-criteria optimization to an easier form. In other words, users may express their preference between the minimal make span and minimal computational cost. The error between developed and real schedules fits within a 15% margin. And developed one-pass PBS-based simulator can sufficiently simulate workflows executions. In the future, I would like to include the information about the cluster utilization to my cluster simulator. So I think, or I hope, it should better simulate the executions in on-demand allocations. So it's allocation where users share resources. So they pay only for the resources they actually use. And I would like to examine more advanced machine learning methods, because I expect that by the time I will collect really a lot of performance data, and I think some machine learning will definitely find its place here, and it could improve the interpolation accuracy. So this is all from my side, and if you have any questions, I'll be happy to answer them. Thank you.
Thank you, Marta. Perfect timing. So do we have some questions in the Slack? Not yet. So my question is, if I may, so the point of the simulator is to evaluate what is the impact of you changing the parameters of the tasks, because the title is Moldable tasks, or sorry, the title is Moldable workflows. Yeah. So if I understand it correctly, you can change the parameters of the tasks to somehow trade between cost and execution time.
Yes.
And then you need to see what is the impact of such changes, and for that you need the simulator, right?
Yeah,
Okay.
Exactly like that.
Yeah.
So,
and what is the and the genetic algorithm is responsible for
finding the execution parameters. So
okay.
It uses task input, which is usually domain size and some other things that are specific, and historically collected performance data, and it tries to find execution parameters for a given workflow. Then it calls evaluator and it says, okay, the make span is like it will cost like it, and optimizer says, okay, it's well, I'm successful with it, here's the execution schedule, or I'm not happy, so I'm going to try to find something better.
How many parameters, not exactly, but what is the number of parameters that are actually being changed? Is it like dozen or hundreds or 5?
You mean on the input?
During the optimization, well,
yeah,
I mean,
well, at this time the optimization is quite simple. It only tries to find number of nodes for a given time.
okay.
But in the future, there may be more things. For example,
sure. Yeah. Okay. So sorry, I didn't mean to interrupt you. I was like, I'm trying to. Sorry, my mind is speaking through my mouth without filtering. Yeah. Okay. Oh, thanks. That answered my question. Any other questions? And the simulation is used to compute proper wave propagations of the ultrasound.
Yeah, that's the executed task or multiple tasks.
Yeah, I mean, okay, so you have this tool which creates some schedule which is very close to reality. So, and then you execute it on Barbara, on the supercomputer. And the output is something which is then used to treat patients in hospital.
Yes, yeah, exactly.
Yeah. Okay.
For example, one use case is how to set the ultrasound transducer. So the medical doctor tries to find some good parameters, but it's a guess at this time. So we try to simulate his guess if he's successful with this treatment or not. So the answer for the medical doctor is only how good is he, how successful with this parameter settings.
Yeah, sure. So yeah, and it's probably patient dependent, like it can be, yeah, sure. His or her weight, blah blah blah. Oh yeah, okay, I got it. Thanks. So,
questions?
If not, I believe we have a coffee break for 15 minutes, and we will meet at, well, 12:15 Eastern Daylight Time. We basically will meet in 15 minutes, and we will have this shorter session with 2 regular papers and 1 open scheduling problem paper. And after that, we will continue with our keynote lecture. So thank you all for visiting the first session, and see you in 15 minutes.